Right. So today we're finishing the chapter 4, and to finish it, we are going to discuss separable spaces. So what is a separable space? Uh, it's a space. So you need a topology because you need the density. So here our framework is that we assume that E is a Banach space. And so we say that E is separable if there exists a countable subspace which is dense in E, right? There's a typo here. Okay. And so we're not going to deal about everything in separable space. In fact, we are just dealing with the following theorem. So if you assume that E is a separable Banach space, then so you take the closed unit ball in the dual space, and then you can find a metric, a distance for which the open sets correspond to the weak star topology. So that means that E prime is metrizable for the weak star topology. Conversely, if you can find a metric in E prime in the dual space for which the open sets are the open sets of the weak star topology, then E is separable. All right, so first, let's assume that E is a separable Banach space. So we want to prove that there exists a metric in the dual space E prime such that the topology associated with this metric is the weak star topology. So let's see. So first, since E is separable, you have some countable subspace which is dense. And so we assume that these elements, this subset, it doesn't need to be a subspace. Actually, it's a subset, and so if it's separable, there exists some elements in E countable such that so I assume that I call these elements AN. And then we will use this AN to define our distance. So actually, our distance will be the following. Okay. So this is our distance. So actually, and so you can check that this defines the norm. So first the question, so first, is this well defined? And is this defines the norm? Or here a distance, and if I take just apply that just at phi1 and phi1 minus phi2, this is a norm, and if I do the difference, this makes a distance. So first, you can check that Yeah, this defines a distance and the norm. Now you have to check, we have to check that the open sets associated with this distance are the open sets of the weak star topology in E prime. Okay, so we are going to prove the theorem. So as we've seen, so since E is separable, so we assume that you have a sequence of elements in E, actually in the ball, is dense in the ball. So this is the closed ball in E for the usual usual norm associated to E. Okay, and then for the distance we consider so for every phi in the unit ball, here it's in E prime, we set so this is a crucial thing. That's the definition of our norm. So we can check that this defines a norm on the ball. Okay. All right. And so if you assume that d of phi1, phi2 equals phi1 minus phi2 is a distance on the ball. This is a norm. You can check that, okay? I let you as an exercise to do at home. All right, so now what we need to do is, so assume that U is, so assume that U belongs to, so U is an open set of the weak star topology. So this means what? This means that U intersection with the closed ball is an open set of the induced topology in the ball. This is classical definitions of topology and results. when you have a Banach space or a topological space, a normed space, you have so you have a topology, and then if you consider the topology on the subset of this space, the open sets are just the intersection of the open sets in the whole set with the subset. Okay, so this is an open set of the induced topology on the ball by the weak star topology. So what we want to prove is that we want to prove that this is also an open set for the topology induced by the distance d on the ball. All right. So first, so now we need to go to get into the details. So now let's phi node belong to U intersection with the closed unit ball in E prime. By definition of the weak star topology, by definition of the weak star topology, there exists an epsilon positive and some x1, xk e such that now I look at the set this is equal to U. Okay, this comes from the definition of the weak star topology. So important, the x1, xk are finite. Okay, so you have to get to remind what we did in this chapter. Okay. So next, for us to prove the results, it is sufficient that we can put a ball centered at phi node in this, and a ball for the distance that we defined. So more explicitly, what we need to do is so it is sufficient to prove that there exists some mu, some positive mu, such that so it's the wall. So let's write it in detail, such that the phi belonging to I prime, such that it's in U. So let's do it. Such that the distance so this is the ball center at phi node and of radius mu for the distance d is included in the set that we defined previously. So I can call it, let's say, V. So V, and so V, there's not the ball, so I need to intersect it with the ball. All right, so now look at that. Look at this expression. So in fact, what I need to do is to ensure this estimate here for a finite number of xi. So I need to ensure this estimate here. All right, so let's write it. So let's write it. And I want to obtain this estimate with a prescribed estimate on D, on the distance D. So if I write here, for example, phi xi minus phi node of xi. So note that those are values in K. So I want to get an estimate with respect with my distance D. So what I need to do is first, I need to go from the xi to the ai, which are dense. So and here actually the AI, I take it not only on the ball, but they are dense on E. Okay, so such that I can do this will be less than phi of xi minus phi of some a and I. Okay. Plus phi a and I minus phi node a and I plus phi node a and I minus phi node of xi. All right, so I choose a and I such that xi minus a and I is less than epsilon divided by 4. Okay, I can do that because my sequence an is dense in E. At the beginning, I chose it to be dense in the ball, but no, I want it to be dense on E, which is the case, which I can do that by our assumption. Okay, next, what can I do? So this term here, this term here is less than the norm of phi. So this is the norm on the dual space. And this is less than 1 because it belongs to the unit ball, the closed unit ball, times xa minus I and a. So this thing, I can make it less than epsilon divided by 4. Same thing here. And now I need to deal with this term here. Okay, but so by definition, okay, by definition, phi of a and I minus phi node a and a and I this is less than. So I want to put here the norm phi minus phi node. But so in the definition of this distance, this is d, which is d. By definition of this distance, I have a 2. So I just need to put here a 2 to the power ni. So if I choose, let mu be less than the max, I don't remember, k of 2 and I will multiply by epsilon divided by 4. Then find my final node. If find my final is less than mu, then this quantity will be less than yeah, I wanted epsilon divided by 2 actually. So this is a detail, it's not very important, but no, I can take it less, but so I want that to be less than epsilon divided by 2. So I just need to sorry, so it's here 1 divided n times 1. So now this quantity will be less. So than epsilon divided by 2. This will be less. So if this is less than mu, this is less than epsilon divided by 2. And at the end of the day, I obtain that we obtain that for all I we have that phi xi minus phi node x is less than epsilon, which implies that we good the ball centered the ball for G. So the ball mu G. So the ball centered at phi node of radius mu for, let's say, let's write it like that, for the distance D, intersection with the unit ball. So this is also the problem. It's included in V intersection V C E prime. So what we proved here, we proved that the open sets of the weak star, every open set of the weak star topology, but on the ball, so every open set of the topology induced by the weak star topology on the closed unit ball is in fact also an open set for the topology induced by the norm, the distance D that we defined at the beginning on the unit ball. Now we need to prove, so we want that those two topology are equal. So we need to also to prove that every open set induced by the distance D is an open set of the weak star topology. Everything here is on the ball. So before going forward, just a detail that you need to clarify. So as you see here, I told you that we choose AN in the unit ball. So for the first part of the proof, at some point we needed AN to be as close as we want of some xk or xi, but the xi are not in the ball. But in fact, the xi you can take it in the ball. So there is some detail. I'm not going back to that, but this works well. Okay. So, but the AN in the second part of the proof, we need it to be in the ball. Okay, we'll see why. All right. So so let's go to the second part of the proof, which is now we need to prove that sorry, any open set in the topology induced by the norm on the unit ball is also an open set for the sigma star, the weak star topology on the closed unit ball. So that's the point. Now we assume that U is an open set in the dual space. And so let phi node belonging to this open space, this open set, and the unit ball. So since U is an open set for the distance D, I can find a mu such that this holds. That is, the ball centered phi node of radius mu is included in U. And so we want to prove that this so we want to prove that this coincides with the weak star topology. So for that, we need to prove that. That is, there exists an open set of the weak star topology. And I take the intersection with the closed unit ball, and this will be included in this one. Okay, so but to do that, so I need to find this x1 until xk. In fact, this x1 xk will be chosen as a1 as some a in the ai's. So how do we do that? So so we have that, but then here I need to ensure that so we have that. So here I use that the AN are in the unit ball. So if I have this one, then the series converges, and I need that. So I need that the series to converge, and so let's end node such that this holds. So since the series converges, I can ensure that for n large enough, this is smaller than mu divided by 2. And so now, thanks to that, I get rid of the problem of the infinite series. So I'm good because my xi's will be my a0 till an0. So next, this is important here. All right, now when you take the series, the whole series here, will be less than mu, and we're done. Okay.